going to look at a few graphs, and also we're going to look at a couple of word problems, at least one definitely. In all sections we have to cover at least one word problem, so we see where this is applicable. And then we'll move on to section 3.3. We're going to refresh our memory on the long division, and hopefully we can get to graphing rational functions. I don't think we can accomplish more in an hour and 15 minutes. Okay, so we know it's a long list, but I will know that I finished when I fill up the table. I'm going to start with a domain. What is the domain of this function? Right, it's a polynomial function. It must be negative infinity to infinity, for sure. Now I have to determine the degree. The degree will be, yes, 3 plus 2 plus 1. X squared times x cubed times x is indeed degree 6. What is the maximum possible number of turns? It doesn't have to turn 5 times. Very good. Awesome. It doesn't have to turn 5 times, but it cannot turn more than 5 times. That's a top. Good. So then you're going to give me 6 zeros or 6 x-intercepts. When we try to solve the equation f of x equals 0, we're finding the zeros of function f of x or the x-intercepts. So negative 2 x cubed, x minus 1 squared, x plus 5 equals 0. You're going to give me 6 solutions. And those 6 solutions are, yes? X equals 0 3 times, so multiplicity is 3. Good.
X equals 1.
Twice, so multiplicity is 2. And x equals negative 5, multiplicity 1. This number plus this number plus this number has to give us 6. They have to, the sum has to add up to 6. Yes? Perfect. So then I know that multiplicity odd will be a cross. Even multiplicity will be a turn. But there is a difference between these two. Multiplicity 1 is a straight cross. Multiplicity 3 is a flat type of cross. I'm going to make myself these notes. So I have a 0, 1, and negative 5. Negative 5, 0, 1. At 0, 0 is a cross but flat. At 1, 0 is a turn. At negative 1, 0, negative 5, 0 is a cross. Obviously, there is no point in trying to see whether this function is symmetric, but I still have to write it. Why this function cannot be symmetric? Because it crosses at negative 5, 0 on one side, but it doesn't cross at 5, 0 on the other to be even. Could it be odd? Yes, it could be odd. But even if you try to find f of negative x, I'm trying to save us some time. So if you try to find f of negative x, I guarantee you it's not going to equal f of x. So the function is not odd, and it's not even. Not symmetric. But I also need to determine, the reason why I didn't determine the y-intercept is because I already have it. When x is 0, y is 0. Finally, I need to determine the end behavior. And that's all we need. And we are ready to graph. How do I determine the end behavior? The degree is even. Because the degree is even, the function either comes from positive infinity going back to positive infinity, or coming from negative infinity going back to negative infinity. Since the leading coefficient is, can anyone read the leading coefficient for us? Negative 2. Negative 2 and an even degree. Is it this? No, it's this. Is that clear? Okay. Ready? Okay, so let's give us the chance to graph, and then of course we will check with the graphing calculator. So first I plot -5, 0, 0, 0, and 1, 0. So I plotted -5, 0, 0, 0, 1, 0. Here they are. Then I look at the fact that the function is coming from -infinity and crossing at -5, 0. It's coming from -infinity, crossing at -5, 0. Then it's crossing at 0, 0. But it can cross at 0, 0 unless it comes to a maximum and then comes back to cross, but it's a flat cross. It's not like this. It's like this. It has to turn again because now it comes up to 1, 0 and turning and going to -infinity. This is the graph of f of x, -2x cubed, x minus 1 squared, x plus 5. I have to put this function in the graphing calculator for several reasons. Number one, I have to check my work, make sure. But also, I need to determine these, the max and the min. Local max, it also happens to be the absolute max, and local min. So I know that this local max is between -5 and 0, and I know that the local min is between 0 and 1. The graphing calculator will ask me for some boundaries. That's why I need to have those ready. So in y equals, clear everything else, anything you have in there, and just plug in -2 x to the third power, now in parentheses, x minus 1 to the second power, and then times x plus 5. I already know, let's go back to the graph for a second. Do we all have this? Let's go back to the graph. I kind of believe that this is going to be a small value here, small minimum, but this one I have no idea how high it would be. But that's okay. I don't want to go too low. So let's say maybe -3 to, I don't know, maybe 50. I have no idea. On this side, I'm going to go to -6, and on this side, I'm going to go to 4. So -6, 4, -4, 20 for now. So I'll go to the window, and we said -6 is fine, up to 4. I have a cheat sheet here that you probably don't. I already see the graph. Okay, and then y minimum. Yeah, 1 minimum, -2 is good enough. And the maximum, look how big this is. I'm going to put 2,000 with a scale of 500. I don't know, maybe I have to go back and adjust again. I don't know. We'll see. Yeah, it's way over 2,000. I shouldn't say way over, but it is. Okay, so I go back to the window, and I'm going to make it 3,000. This should do it, but I'm not sure. No, it doesn't. Okay, maybe 4,000 will be enough. And this time I would like to change the negative also, because I would like to see what happens here. So maybe we can just take a look and say -1,000. So it's crossing at -5, 0. Look at how, see the difference between this. So do not assume that this is the same with the x-axis. It's not. But see how this is crossing here at -1? Not like this, but like this. Yes, please.
We can't see what you're doing.
Oh, yes, of course you can. You don't have X-ray vision? Sorry, my apologies. I'm sorry. Let me go back. So we have the function, right? Okay, so going to the viewing window, I put -6 to +4. That's really all I need with a scale of 1. But on the y-axis, I went from -1,000 to +4,000 with a scale of 500. And then I clicked graph. So see, this is a regular cross at -5, 0, but at -1, the function does not cross straight, but very slowly. Now this, we know it's wrong. I wanted to determine this, the coordinates of the maximum, and then I'll come back and zoom in here. So obviously the maximum is between x equals -5 and 0. We go to second and calc. From this menu, we will choose 4, which is maximum. I have to give a left bound, which is -5. And the calculator says, okay, I'm going to start from here. And the right bound, I'm going to say -1 or 0, that's fine. So the calculator will find the maximum between this x value and this x value. It's asking me to guess. I press again, enter, I don't care to guess. So the maximum is -4.1. I'll put it back in the table. I'll show you in a minute. -4.1, 3226.91. Now I have to zoom in and determine that minimum. So I'm done with this part. So I'm going to zoom in right in here. I only care to see between -2 and 2 and between -1 and 1. So I'm changing the viewing window between -2 and 2 with a scale of 1, and between -2 and 2 with a scale of 1. So here it comes. It crosses at -1 very slowly. Why can't I see negative? It was at -5 actually. Oh, yeah, because it's completely outside of the way. Yes, of course. So it crosses at -5 over there, goes to a maximum, and then it crosses very slowly at 0, coming to a minimum, and then turning at 1 again. We knew everything. We graphed it correctly. However, we just have to determine this minimum. So now the minimum is between 0 and 1. So I go back to second and calc. And this time I choose number 3, which is the minimum. And the left bound is 0. The right bound is 1. I want the calculator to determine the minimum between 0 and 1. I press enter because I don't want to guess. And I get the minimum as 0.61. And the y value is -0.39. So I put those in the table. So -4.1, 3,226 is this value. These are the coordinates of the absolute max and relative max. And the other one, 0.61, comma, -0.39 is this. It looks difficult, especially this is the first problem. But once we look at a few problems, you're going to say, oh, it's easy. I had the same thing happening to me about an hour ago. Students said, oh, this is difficult. One of the students spent like 10 minutes, 15 minutes, maybe half an hour here with me, and he said, that's easy. I don't want you to spend too much time on it. However, I would like us to look at the word problem, and then we'll go back to more graphing. Any questions for me right away? Anything you'd like to ask? Any questions? Okay, so let's take a look at the real life situation. Here's a graph. During a diagnostic evaluation, a 33-year-old woman experienced a panic attack. Oops. A few minutes after she had been asked to relax her whole body. The graph shows the rapid increase in heart rate during the panic attack. So let's take a look. So let's just try to understand the graph first. Minute 1, up, down, up, down. First question. For which time periods does during the diagnostic evaluation was the woman's heart rate increasing?
From the 8th, well, from the 1st minute,
From 1 till
4th minute,
to the 4th minute. Very good. Union from
8th.
till 10. Very clear. Exactly what we studied in chapter 2. Okay. For which time periods during the diagnostic evaluation was the woman's heart rate decreasing? Between 4 and 8. Union between 10 and 12. Do we agree? Okay. Part C. How many turning points, max min, that's what it means, occurred for the woman's heart rates during the first 12 minutes? Up, 1, down, 2, up, 3, and down. Turning points meaning from up, down, that's what 1 point. From down, up, that's another point. From up, down, another point. So how many turning points? 3. The next question, suppose that a polynomial function is used to model the data displayed. What will be the degree of the polynomial? Yes. 3 turning points. The minimum degree has to be 4. Can it be 10? Yes, it can. Of course. But minimum 4 because it has 3 turning points. Right? If the degree is 4, how many turning points are there? 3. Good. So minimum 4. For the model in part D, should the leading coefficient of the polynomial function be positive or negative? Yes. Even degree, it goes to, of course, we're not going to talk about negative infinity here, but yes. Degree 4, it has to have, in this case, it has to have a negative leading coefficient. Do we agree? Okay. Use the graph to estimate the woman's maximum heart rate. Where was the maximum heart rate? Not where. How much is the maximum heart rate? 115. 115. Where did it occur? When?
10 minutes.
Exactly. 10 minutes into the experiment. Okay. Or evaluation. Use the graph to estimate the woman's minimum heart rate. What was the minimum heart rate? 62, 63, 65. Very difficult to read. I agree. When did this happen? 8 minutes into the evaluation. So there is nothing else that fits here, the data that we see, but a polynomial function, minimum degree 4, even degree with a negative leading coefficient. So this is an application of what we just studied. Ready to graph another one? So we graphed an even degree. Would you like to choose an odd degree now? The procedure is the same. But let's choose an odd degree, or you would like to continue with another even degree. It's up to you. Odd degree, perfect. Here they are. Let's choose an odd degree. It can be from the non-factored, or it can be from the factored. We used one from the factored. We picked one from the factored. Let's pick one from the non-factored form of a polynomial. Degree odd, like 3 or 5. Which one? 49. It's degree 4.
So that's
48. It's degree 4.
51.
51. It's degree 5. Excellent. So let's take a look. So 51 on page 378, and this is f of x, 6x cubed minus 9x minus x to the 5th power. You know me quite well by now. What do you think I'm going to do first? Of course. Absolutely. I refuse to work with something that is not in the correct order. Good. What will be the next step? Factor our negative x, indeed. The greatest common factor and the negative leading coefficient. Good. So what do we have in parentheses? X to the 4th minus 6x squared and plus 9. Very good. And I see that this can be factored easily. Can anyone tell us how to factor? You can say, use the substitution, as you taught us in chapter 2. Yes, I could. Is there another way of, without using the substitution, can we determine the factored form? Bless you. Is there a way of factoring x to the 4th minus 6x squared plus 9? This is the formula that we discussed on the first day of classes. I gave you a handout. Anyone remembers?
X squared minus 3 times x squared minus 3.
Excellent. Indeed. X squared minus 3 squared. Thank you. Good. Degree. That's all I needed for now. I'm getting it ready for finding the zeros or the x-intercepts. What is the degree again? Excellent. What is the maximum possible number of turns? It doesn't have to turn 4 times, but it cannot turn more than 4. Perfect. What about the domain? Yes, it's a polynomial function. Very good. What about the end behavior? It's an odd degree, and the leading coefficient is positive or negative? Negative. So is it this case or this case?
First one, negative 50 to infinity.
So because it has a negative leading coefficient, it cannot be increasing, right? It would be decreasing. So say it again. So infinity to negative infinity, indeed. Good. We're going to talk about symmetry in a minute, but I would like to find the x-intercepts and their multiplicities. Again, what was the degree? Good. How many solutions we have to come up with? Excellent. So the x-intercepts are determined by setting f of x equal to 0, negative x, x squared minus 3 squared equals 0. We have to do this in 2 steps. Obviously, one solution is definitely known to be x equals if 1 is 0, then 1. But since 1 is not 0, then indeed. Multiplicity 1. So now we are here with x squared minus 3 squared equals 0. On which one? The multiplicities, you mean?
I'm saying that generalize all these things. It doesn't make me want to overanalyze it or complicate it.
You mean the negative x in front, you mean? What are you...
Don't mind.
No, I'm really trying to understand, is maybe I misunderstood something. Please.
No, when you're asking us what our first solution is.
Yeah. So you all you have to say is using the zero product principle, right? This is something that we've been using all the time. A times B times C equals 0. There are three options. Either A is 0, or B is 0, or C is 0. So I'm hoping that when my students see something like this, they will never say x equals 1. That's my hope. But if I have to explain this again, I will, as many times as needed. Because -1 times whatever can never be 0. Right? So this must be 0. It's the first factor. The first factor is 0, means x equals 0. If the second factor is 0, then I have this. Is this better? Okay. So I have to solve this, but I will have x squared minus 3 equals 0 twice. So I'm talking about this one first. How do I solve such an equation? Again, we've done this before, many times before. So how do I solve x squared minus 3 equals 0? Yes, but it's not ready. Yes, indeed, the square root, but it's not ready yet.
First you have big numbers.
Yes. So then I have this, and I take the square root. And how many solutions again I have to write? Exactly. Yes, exactly. So, of course, when I solve the other one, the second one, which is the same thing, I will still get plus or minus the square root of 3. So we have x equals the square root of 3 twice. And we have x equals negative the square root of 3 also twice. The 2 plus 2 plus 1 have to add up to 5. So I only solved one of them, but it's the same with the other because they're identical. So there are 5 total solutions, 1 of 0, which means a cross, 2 that at the square root of 3 with minus, so this is a turn, and the square root of 3 with plus, but there are 2. So these 2 are turns, and this is a cross. We're done. All we want to determine now is whether the function is symmetric or not. So remember f of x. The factored form is this. And if I plug in negative x times -1 will be x. Negative x squared will not change. It's still x squared minus 3 squared. And remember the 3 questions. Does this equal f of x? If it equals identical, it's identical to f of x, then I'll say even. If it's the opposite of f of x, then I'll say odd or not symmetric. I have to choose one of these 3. Is this answer identical with the original problem? No. Is this answer identical with the opposite of the original problem?
Yes.
Yes, awesome. Well done. So the function is odd. Now we're ready to graph. And you can say, how are you going to graph the square root of -3, comma 0? I'm going to approximate, of course. I can't. So negative the square root of 3, or the square root of 3 is 1.7. So 1, 2, I'm going to say somewhere here. Then the 0, 0. And then on the other side. So I have this point. I have this point, which is also the y-intercept, and I have this point. So the function is coming from positive infinity, and it will be tangent. It will turn at this point. Okay. Is that okay? Then it will cross at 0, 0. But it's a regular cross. Okay. So it has to come to a maximum and then just simply cross. Now I don't have to look at the rest. Why? Well, I know the function is odd. So whatever I have here, I have to have here. So a copy over the origin. And this is the graph of f of x. Very good pick. Thank you for picking this. It's very interesting. So this is negative x to the fifth plus 6x cubed minus 9x. So, of course, I do not know this, and I do not know this, but everything else is known. So I'm going to find the maximum between negative 2 and 0. So let's put in the function. In y equals, we have negative x to the fifth. Then we have positive 6x cubed. Then we have minus 9x. And I know the viewing window should not be more than negative 4 to 4 and negative 4 to 4. Although I see here, but that's the previous viewing window, so I don't know. I'm going to say negative 4 to 4. I'm going to use this window, the scale of 1. I can always go back and adjust. It's not a big deal. And let's see what we have. We know it's coming from above. We know it's turning. We know it's crossing regularly, straight cross. And it turns at the square root of negative the square root of 3. It turns again at the square root of 3. It crosses at 0, 0. I don't see those 2 points, so I have to adjust a tiny bit. So y minimum, I'm going to put it to negative 8, and y maximum to positive 8, in the hope that that would be good enough. If not, I'll go back and adjust it again. It's not a big deal. Okay, it was good enough. So this is our graph. We know that this is the turn, and this is another turn, a minimum, local max. But we don't know this local max, and we don't know this local min. We know we are looking for this between negative 2 and 0. So we are looking for a maximum, which is 4, between negative 2 and 0. I don't want to guess, just give me the maximum. And it gives us negative 0.78, negative 0.78, and 4.46. Can anyone without calculations give us the other one?
7.8.
Excellent. Yes. Because we know why were we able to cut back on the time spent on this? Because we knew it's symmetric. Otherwise, we could have not guessed. That's why it's important to know whether a function is symmetric. Will functions in general be symmetric? Not really. But if it is, it's nice. If a function is symmetric, it's really nice and easy to work with. Perfect. It took me a lot of time to explain all this, but do we feel a little bit better? It's up to you. Would you would like to choose another? I'll be more than happy to show another, either even degree, odd degree. They're all the same, just minor changes here and there, but it doesn't matter. Would you like to choose another?
Yes.
Very good. Would you like to pick? Pick anything you want. So again, these are not factored. These are, I need a step to factor, but that's why we reviewed factoring at the beginning of the semester. And all these are already factored for us. It's up to you which one you want to choose.
57.
We want to choose 57. This one? Excellent. Can anyone tell us the degree of 57? 2 plus 3 plus 1. Excellent. 6 indeed. Great job. Do you want to choose another 6? We already had a 6 degree, but it's fine. I don't mind. Yeah? Yes?
Okay, we can take the last one. It's the last one.
Which one?
The last one.
This one? Okay. So x plus 3, x plus 1 cubed, and x plus 4. What is the degree?
5.
So 3, 4, 5. So we wanted an even degree. So it's fine. It doesn't matter.
Want me to be, I'm sorry.
Nothing wrong.
63.
63. 2 and 1 and 1. Perfect. Degree 4. Let's take a look. Is that okay?
Yes.
Oh, yeah. Of course. Thank you. I was going to check my video. I'm pretty sure I started. Yes. Okay. 63 on page 378. And we have f of x equals negative x minus 2 squared and x plus 4 and then x minus 1. Very good. Please use the table that I showed you. If not, invent your own table that summarize the information. It will be much more difficult to graph a function without summarizing the information. So please, or adjust the table that I showed you, or create your own. It doesn't matter. It can be vertical, it can be horizontal, but you have to present all the information there, please. Okay, so let's start with the domain. Obviously, the domain is right because it's a polynomial function. Good. What about the end behavior? Let's discuss the degree first. The degree of this polynomial is, yes, indeed. Max terms, excellent. End behavior, right, because it's degree 4, it behaves like x squared with minus in front. Excellent. Perfect. Symmetric? No. You'll see, we will write it at f of negative x. It's guaranteed it will not equal negative f of x. It will not equal f of x. That's all I want you to write, not symmetric. You'll see why for this function. Okay, so let's find the x-intercepts, or the zeros. My lab math is calling them zeros. That's fine, but it means the same thing. So we have f of x equals 0, negative x minus 2 squared, and x plus 4, and x minus 1 equals 0. How many solutions will you give? Exactly 4. Excellent. So please tell me or give me those solutions. The form is factored. I mean, when it's factored, we should only need like 3 seconds to write those solutions.
2, negative 4, 1, 0.
So, say it again.
2,
How many times?
2,
Good. Multiplicity 2.
negative 4,
Yes.
then 1,
Yes.
1.
Yes. Good. 2 plus 1 plus 1. Does that equal 4? Yes. We obtained all of them in the correct order. Negative 4, 0, 1, and 2. Multiplicity 2, what does it mean? Multiplicity 1 will be just a simple cross. So only 2 is a turn. Cross, cross. Let's find the y-intercept and we're done. So it is an important topic, but not the most important one. So I don't want you to spend more than 3 minutes on a problem like this, please. Okay? So let's plug in 0 together. 0 minus 2. Negative 2 squared. 4 times negative 1. Negative 4. 0 plus 4. 4 times negative 4. Negative 16. 0 minus 1. Negative 1 times negative 16.
16.
That's it. That's it. Done. Let's graph it. I start by plotting the points. Which points am I talking about?
The X-intercept.
Yes, and the y-intercept, yes. -4, 0. 0, 16, I'm going to use a unit of 4. 4, 4, 4, 4. Very good. And 2, 0. Excellent. Great job. Thank you. So now, it's coming from -infinity and crossing regularly. Nothing fancy. Now, I wanted to explain one thing before I continue. When we graph a polynomial function, the graph is smooth. It's a smooth curve. If I have to twist my wrist and do something like this to graph, something is wrong. Okay? So I don't know whether the graph will do this or it will do this, but this is already I have to twist my wrist to graph it like that. I have to twist my wrist to do this and then come back down. And how do I do it? It's not even a function. So most probably the graph does this. There are other options, right? This or this. But then how will it cross at 1 and 2? So most probably this is the situation. We'll see. You just picked the problem. I haven't looked at it. I have no idea. So then it crosses at 1, 0. Very nice, smooth. My wrist didn't hurt. It has to come to a minimum because it turns again at 2 and then go into -infinity. I don't think it's this. It would be very difficult to come back. I don't think it's this because it's also kind of difficult to come back. My wrist hurts. So this is our f of x, negative x minus 2 squared, x plus 4, x minus 1, and of course I have to determine the local max. In this case it's also absolute, and the local min. Very good pick, very interesting graph. So let's take a look. So please plug it in. Clear whatever you have in there. And let's put the minus, in parentheses x minus 2 squared, and then x plus 4, and then x minus 1. Ready? Okay, I'm thinking about the viewing window. So obviously from the graph that we just graphed, the action on the x-axis happens between -6 and 4. And the action on the y-axis, I know very little under the x-axis, but it may be very high on the positive side. So I'm going to give it a shot. I'm going to say -6 to +4, that's okay, with a scale of 1. I don't want too much of y minimum. -4 is way more than I need. But look at this. The left-hand side, I'm not sure. I'm going to put 2,000. I'll come back. Not a big deal to adjust the viewing window. It crosses, oh, I went way too far. Okay, so I go back. I'll put 1,000. Or maybe just 500. I'm going to try 500 with a scale of 50. Okay, not a perfect graph. I'm going to adjust again. Okay, I'm going to say just 200. Y minimum, let's say -50, and Y maximum, let's say 200, with a scale of. Okay, it should be pretty close. Okay. Okay. I completely disagree with this. This is deceiving. We know that's not the case. It crosses at -4. It goes to a maximum as expected. It crosses at 0.16. It crosses again at 1, 0. It comes down to a minimum that we do not see. I'll adjust the viewing window and we will see it in a minute. And then it turns at 2. Okay? So I'll adjust one more time. Y minimum, I'm going to make it -5. See what happens. And 200 can be 150. Okay, that's good. I don't see this yet, but that's okay. We'll zoom in a moment. So let's find this maximum between -4 and 0. So it's a maximum which is 4. Between -4 and 0, and I don't want to guess. Just give me the number. And that is -2.6. And the maximum is 106.6. Since it's kind of difficult for me to see both at the same time, I'm going to right now zoom in only here. So I'm changing the viewing window between 0 and 3. Y minimum -1, Y maximum 1, with a scale of 1. Let's see. Beautiful. Beautiful. It's coming from that 16. It crosses it 1, 0. It's coming to a minimum, but it's a tiny minimum. It's between 0 and -1, right? It comes back to 2 to turn and go to -10. Now I can determine that minimum. It's between 1 and 2. So second and calc, I want the minimum this time. Please cooperate. I want the minimum, and it is between 1 and 2. You have to give these bounds to the calculator, otherwise the calculator doesn't know what you're looking for. So it's 1.34 and -0.79. So -2.6, 106 is this. -2.6, 106.6. And this one is 1.34, -0.79. Of course, my graph is not on scale. How can this be 100 and this be 0.7? But that's good enough. We don't want to spend too much time on this.